Good morning. My name is Tyler, and I wanted to go over my final project. So, in C Sharp, there are three data structures that I find to be important. There are many more, but these are the three that I wanted to go over. So, the first one is queues, second one is sets, and the third one is trees. So, for queues, queue is a linear data structure. You can kind of think of it like a line in a grocery store. The first person to get in the line is the first person to get served. And if you're, stepping in a line that has 50 people in it, then you're in 51st place and you will get served after 50 people get served. So that's the way that queues work. It's called first in, first out. There is also something called a priority queue. You can think of it kind of like an amusement park. People get in like normal, but if you have that I'm important pass, then you can kind of jump to the front of the line. Although you can have multiple levels of priority. Lists allow for arbitrary insertion and deletion at any position. So I can say, hey, put this in the 41st place. But queues are meant to keep track of order so that they can be efficient for insertion and deletion of items, or enqueuing and dequeuing. They can be used for task scheduling, managing print jobs. Like if you send 14 things to the printer, they're going to print in the order that you sent them. Breadth first search, that's for graphs, network request handling, and video playback. So all sorts of things they're used for. For their operations, a lot of them are meant to be O of 1. That's why they are made, is to make them super fast to get through. Searching can take up to all of the elements of the queue because you search from front to back. That's an array-based queue. If you have a linked list queue, which just keeps track, essentially it like an element in the queue keeps track of itself and then where the next item in the queue is. So they don't have to be all stored in one array that's in one spot of memory. They can just be wherever. And then if an item is added, then the previous guy will say, hey, this is where the next guy in the list is. And then if you wanted to reverse it, just switch all those pointers around. And then priority queue has a little bit different operation speed. Searching is still the same. Peeking at the front element is the same, but because you might not be taking the first item out of the queue, because you might be searching for something with a specific priority, it does take a little bit longer up to log n time. Then for an example problem, this is receiving incoming calls. You got to answer them in the order that they arrive. So you want to use a queue. When an agent is available, dequeue the first call, and then print the order in which they're answered. So example code. Essentially, you just enqueue the three items. So Alice calls first, Bob calls second, and then Charlie calls third. Then process the calls in order, and then you just dequeue the item, and then it'll say, hey, I'm answering this call. So if I run this, answers Alice, then Bob, then Charlie. And that is just using the built-in queue data structure. So a problem to solve. Design a task scheduler that processes tasks in order but allows higher priority tasks. So this is a priority queue. And then if they have the same priority, first in, first out. So the template looks like this. So you need to add a task to the queue with the priority. And then to dequeue, remove the highest priority task. And then this is just checking if it's empty. I don't believe I do use that. So then you in-queue a couple things with priority. There are two of them that have the same priority, and then there's a lower and a higher priority. And then you just need to process them. And then the solution for that so in order to enqueue an item, if the priority is already in this dictionary of priorities, then you get that value, then update the dictionary with that new value and then queue it. Oh, come on. In order to dequeue the value, if there's nothing in the queue, you can't do it. Then the highest priority, you take the max key of the dictionary, and then the list of tasks is just the dictionary of that highest, the list of tasks from that key in the dictionary. There we go. And then you dequeue the specific task from that list if it contains more than one thing. Then if there are no tasks left with that priority, then just remove that key and then return the task. So then here you enqueue those four things and then you just dequeue them. But that will dequeue them in the correct order. So system update is the highest priority, so that will happen first. Then the virus scan and the backup files in the order that they were enqueued, which is correct. And then you fetch the email, which is the lowest priority. So there you are. That is an overview of queues. Then sets. So a set is all unique. That's the biggest idea, is that nothing in a set can be duplicated, and they don't have an order. Sets are used in math all the time. They're used to represent distinct objects. So like if you have any set of items that you don't care how many of them there are, you just want to see all the different ones, then you can use a set. And the application is the same in programming, but the big thing is that they are efficient. And a lot of languages have built-in sets. So lists, you can have as many of the same item as you want, and then you can always say, hey, I want the fourth element. In sets, there are no duplicates, and you can't grab the fourth element. You have to search by the actual item. And then in order to check if an item is in a list, you just have to search through the whole thing. Just next, next, next until you find it or you don't. So that's O of n. And then to check membership in a set, it's actually O of 1, because it just stores that location, knows where it is. And so you can always say, hey, there it is. Or I don't have that, and then it doesn't, but it still takes O of 1. And then insertion time is actually O of 1 for both. You just tack it at the end or insert it into the set. Lists are often used for ordered data, and then sets are used for unique data, which we've already talked about. So uses for sets. If you have a list with a bunch of duplicate items and you want to say, I don't want the duplicates anymore, then you can just do set of that list. It'll get rid of all the duplicates. And then, as mentioned above, it has that fast membership checking. And then it also applies those math operations from above. You can handle unique values, like enforcing unique keys. So like with that queue thing that I did, if I wanted to use a set for that dictionary, obviously within a dictionary it wouldn't make sense, but in that dictionary, it's important to only have one key of the specific priority. And so if you had something similar that wasn't inside of a dictionary, you could use a set to say, hey, I need exactly one of each of these and I can't have duplicates. And then like a tagging system, an item can belong to multiple categories of things. So insertion, deletion, and membership check we went over above, but then union, for a set, you go through and combine the two. You take everything that is in both of them and combine them, but because it's a set, if something is in both of them, then it is only added once. But you do have to go through all of the items, so the length of A and the length of B. Intersection, you just take the things that are in common between the two. And so whichever one is smaller, the length of A or the length of B, it will take up to that amount of time to find. Well, it will take that amount of time to find all of the items that intersect. That's because it takes the smallest one, because if every single item in A is also in B, then you just have to go through A, and then if B is larger, then it can't be in A because you've already gone through all of A. And then the difference of A minus B is just the length of A. Example problem, given a list of email addresses, and you just need to get the unique ones. So example code, you just have a function, or I guess a method. It is a function that just grabs the unique emails. So it just creates a hash set that is C#'s built-in implementation of a set. And then it just iterates through that email list, wraps it in a list, or wraps it in a set, and then returns a list version of that set so that you can print it out. So the set is remove the duplicates, and then this just wraps it in a list. So then you have Alice and Alice. Those are duplicates. You want to get rid of them. Well, you want to get rid of one of them. So it should just print out Alice and Bob. And it does. So that is the example one. And then for the problem to solve, analyzing customer purchase data, you want to grab the common items that both customers purchased and the unique items that each customer purchased. So the template, customer A purchased a laptop and a mouse and keyboard. Customer B purchased a monitor and a mouse and keyboard. So then you want to split apart, what are the common purchases, what are the individual purchases, and then grab what they each purchased. Well, this is grabbing all of the things that they purchased. This is where you actually do the computations, and then this is the unique stuff. So then in order to solve this, so this is the same thing. These are the things they purchased. That writes what they purchased. And then to find their common items, you very much like before, just create a hash set with the items from the intersection of customer A and customer B. And again, the intersection is what are the things that they both have inside of them. So they both have mouse and keyboard. So the common items are mouse and keyboard. And then create another set for each customer that is the things that are unique to them. And you do the same things. And then except is essentially the minus. So take out the things that they have in common. So unique to customer A, they have a laptop and a mouse and keyboard, but since customer B also has a mouse and keyboard, then it takes out mouse and keyboard. So this should just be laptop, and customer B is the same thing, but just a monitor. So then it'll print out all of those things. And if I run that, it does do that. So these are the things that they both individually purchased. These are the common items, and these are the unique items, and that is what we expected. So that's an overview of sets. And then the last one is trees. So a tree is, you can think of it like a file structure in Windows. This is a tree over here. You have data structure 1 example that has children. It has a bin folder, and that's got stuff in it, a couple folders. You've got an object folder, has some stuff in it, and you can go deeper and deeper and deeper and deeper, have a bunch of nested folders. And that is a pretty complicated example of a tree, but that is what they are in general. So it's a hierarchical data structure with nodes connected by edges. So a node would be like this folder, and then the edge says, this is my child. The bin folder is the DS1 example folder's child. So that's the edge. They're widely used for all sorts of things. They aren't linear, like lists and arrays and queues and stacks and everything like that, because they can split off in many different directions. So it consists of a root node, in this case, final project folder. That's the starting point of where I am right now. And then it has all these different children. So like all of these guys are children of that root node. Edges, like I said, connect them. And then leaf nodes, this solution file has no other children. So it is a leaf node, which is just a final node that doesn't have children. A binary tree is a common type where it has at most 2 children. So one node can only have a left child and a right child. Binary search tree is a special type of binary tree where the left child is always enforced to be smaller than the parent, and the right child is always enforced to be larger than a parent. So like if you had, here. So like the 4, its left child is guaranteed to be smaller, so it's a 2. Its left child is guaranteed to be smaller, so it's a 1. But that 2's right child is guaranteed to be bigger, so it's a 3. You get the idea. Everything on the right is bigger than its parent. Everything on the left is smaller than its parent. So yeah, that's a binary search tree. Trees are all over the place. So file systems, like I talked about, databases, AI and decision making, compilers, network routing, all sorts of things, all sorts of applications like that. They're used for efficient searches, hierarchical representation. The folder structure is a good one like that. Sorting and searching, so like heaps for priority queues. Auto completion and dictionary application. This is a special thing called a trie, special kind of tree. So like when you're typing, if you type a B, it knows that you're not going to type cat. And so it knows, oh, he's going to go somewhere like this. So I'm going to recommend him words that start with B. If you type BA, then it knows you're not going to type book. And so it's not going to go this way, it's going to go this way. So this is BA. You could type BAG or BAR. And so you want to recommend, well, he can type bag or bar. So I'm going to recommend both of those. So that's what a try would do. It keeps track of where you are, and then, auto-completion is just one application of those. But that is, where did I find it? Oh, there it is. So that's a try. And then, decision-making systems like that. Auto-completion is sort of like a decision-making system. Anyways. So inserting into a binary search tree, because everything has to have at most 2 children, you are going to, like, every level you go down the tree, you're going to cut the amount of remaining operations that you have, the remaining levels that you have to go down. Well, for every level that you go down, you're cutting off half of the options. So, like, if I go left here, I can guarantee I'm not ever going down 4's right children. I'm only going down 4's left children. So that is why it has a log n average, because you're cutting the amount of values to be searched in half every time. But because binary search trees don't have to be balanced, you could have 4, 6, 7, 8, 9, 10, 11, 12. You can just keep going down. It could take up to O of n time. And deletion, same kind of idea. Search, same kind of idea. And then traversal to exit or to navigate through every item in the tree. It needs n because you need to see everything. Balanced binary search trees, there are a couple of trees that enforce balance. So, like, if I were to insert a 9 here, it would whip this 8 up to where the 7 is, set the 7 to its left child, and then insert a 9 here. So it would be as balanced as possible, just so that, I wouldn't have 4, 6, 7, 8, 9, 10, 11, 12. It would try and keep things looking as much like this as possible. So that makes it as efficient as it can be, O of log n, for almost everything. But then traversal does still require all of the steps. So example problem. You're given a binary search tree and a target value. Write a function to check if it exists in the tree. I guess I can go through the instructions. Start at the root. If it matches the target, it's true. If it's smaller, move left. If it's larger, move right. If it's nothing, or if there is a node that doesn't have a value, return false. And that's important because if a node doesn't have children, then they are set to be null. So a node by default has a value. It doesn't have left and right children. It has children, but they are null by default. You can update those to be not null, which is what makes a tree. So then for a tree, in order to search the binary search tree, if the root is null, then there is nothing, which is, you're checking this because it's recursive. If the value of the root is the target, then it's true because you're searching this node for this value. Because this is a binary search tree, if it is less than the value, if what you're searching for is less than the value, then you go left. You return, this is return false if the left node is null. And then this is search the left for the target. So if the left node is null, it'll return false. But if the left node does exist, then this will be true temporarily until this returns something. It'll recurse until it either finds nothing or finds something. And then, it's true, it's true, it's true, all the way until this finds true. Then it'll unwrap all the way and return true. Otherwise, it's in the right tree, it'll do the exact same thing. So this creates that tree where you have the root node is 10, its left child has a 5, its left child is a 2, right child is a 7. So if I come back here, that's like 10, 5, 2, 7. And then the root's right child is a 15. So all of these three are gone, but this guy's a 15. So then you search the tree for a 5. And since 5 is in there, it'll output true. Search for a 20. It's not in there, so it'll output false. So then I come here and run this. True and false. Alrighty. And then this is the problem to solve, given a binary tree, write a function to determine its maximum depth. So in this case, it'll return 4, because there's the root, 2, 3, 4. If this 8 wasn't here, then any of these would be at the third level of depth. So that would be 3. So the template, you have that same tree node class. And then this tree is this tree. So this right here is a code representation of this exact tree. And then you just need to write that max depth. So find it here. And then in order to solve that, this is the same thing. So this is another recursive guy. It'll just add 1 every time it goes down a level. So if the root is null, so if it gets to a point where a child node becomes null, then it doesn't have a height at that point. You're not adding a height for a non-existent child node. You don't get to 8. 8's child is null. You don't add 1 there. But then you take the max depth of the left root and the max depth of the right root. Again, if the right root is null, it will just return 0. But then you will just recurse through everything, so you will navigate through the entire tree. So this is an O of n operation. And then you'll just add 1 for every level. So you'll start at 4, and that'll say 1. You'll go through its left tree and its right tree. Eventually you'll find out that 4 to 6 to 7 to 8 is the max depth. So it should print 4, output 4. So if I come here, max depth 4. That's funny. So yeah, that is an overview of a couple of data structures in C#. Thank you for coming to my TED Talk.